Cristina Chiappini. We met a long time ago when Cristina was doing her PhD and I was doing my master thesis in Trieste, both with Francesca Matteucci. Then she moved to New York at the Columbia University for her first postdoc, and then again back in Italy, in Trieste, at the observatory as a researcher. And then she changed country in Switzerland and Germany, where she's now in Potsdam. And she, of course, worked on chemical evolution, large surveys. She's involved in, she has been involved and she's involved in a number of large spectroscopic and photometric surveys, just to mention foremost. And she will talk about, in particular, metal poor stars and galactic archaeology. So the stage.
Okay, so thank you everybody. First of all, I apologize for changing your seminar of time. There was a miscommunication with family issues, so I had to come now and we will have to leave. So I will not be here to exchange with you, but I will be here a full week during the conference that will be organized here in the end of May. So I will be here from Sunday to Friday, so we can then talk. So I I never managed to give a similar talk as I gave before, so I tried to change it and to make it more broad so that it could maybe be interest for more different groups and interests. But of course, the focus is on ages, and it's essentially this fantastic epoch that we are living in galactic archaeology. We say galactic archaeology because we can use the stars as fossil records of the story of the Milky Way. And we hope that by learning something about the story of the Milky Way, we can also learn about other galaxies, even if the Milky Way is one galaxy. But it's only here that we can, almost only here, there are other exceptions, that we can really measure individual stars and get the full, what we say, 6D phase space information for the stars in the Milky Way now with Gaia. And so velocities, positions, distance, and then also chemistry, individual chemistry for each star, and hopefully ages. That is the more tricky part. No? And so my idea is, as I said in the abstract, was to give you a general idea of these amazing data sets that we have and how we can use Gaia to construct a 3D vision, a 3D maps of the Milky Way, not only on sky, but the 3D, by knowing the distance and therefore the extinction. And then focus on some subsamples for which was possible to compute ages. And then when we find a one different thing or a new constraint for the Milky Way using age, the worry is always on the quality of these age. And if I see the same answer from a different data set that has used a different technique. So that has always been our goal. And as I was also the project science of Foremost during the first phase of Foremost, when we were still in competition with moons, even though we want both to be reality. The good news is that both are going to be reality. And so I will also, a lot of this work is also in preparation for what is coming in 2025 with Foremost. Okay, so of course we don't work alone. We have several collaborators. There's always somebody missing. And it's people involved in surveys in our Star Horse team, which is a Bayesian code. We have a spectrophotometric code we have been using to obtain distance, and also the group here on seismology. So start with the basics, and why I'm showing this figure is our galaxy cartoon seen from above, and this time is not the usual cartoon that we always show from NASA. But it's a cartoon made by ESA, the more recent one made by ESA. So that's our position. That's how we see the bar of our galaxy with an angle. And this is what we think we understand about our galaxy today. So that's an updated version of this figure that you are, is nice to use. So the galaxy, here I'm just showing you a simulation. I'm not a person doing simulation, but I'm really following a lot what's going on in the simulation world. And this is just to say that the disk, of course, is a very complex thing. Lots of things are happening. In the gas is also a complex thing. And then you are forming this bar, you have gas flows, you have this ring in the inner part. And all these, of course, change things, not only in the inner parts of the galaxy, but in the full galaxy. And I'm not showing here what's going to happen to the stars, but apparently or less known, that the interface, the interaction between spiral arms and bar can provoke what we call radial migration. And that's what makes this whole story of trying to set up the history of the Milky Way more complicated, because the stars can be born in one place, move to another place, and they will just be in a circular orbit like if they were born in that particular place. And so the only way you can tell is by matching the age and the chemistry of that star a posteriori in our galaxy. So this is a simulation for an isolated disk. Of course, the things, and this is this recent beautiful paper with JWST images showing from outside the galaxy, we can see this complexity in the gas. From the Milky Way, of course, it's much more difficult. So this is what we think maybe is happening also in our galaxy. And of course, these galaxies are not isolated. Our galaxy is not isolated. So that is also the cosmological scenario in which we are inside, and we are bombarded by other galaxies. And we know that Gaia have shown clearly that we had Gaia Enceladus impact with our galaxy, which was a quite massive galaxy, something like 10 giga-years ago, 10 billion years ago. So how to model this? I mean, you say, why do you need to understand the full picture to understand what's going on with a star in the solar vicinity? Well, you see that there are relations to the big picture, and that there are difficulties in simulate completely in detail all the scales and with all the different tools. And that's why it's nice to have different approaches at the same time, cosmological, non-cosmological, non-cosmological with more detail in gas, and with different also resolutions. That's very important. So this is the map of Gaia EDR3 on the sky. You are of course all know about this. So just the number count of stars is the stars in the sky you see is so beautiful. Every time I look, I find it beautiful. But what we want is to map the galaxy. So it's not enough to look there that way. We need some things. We need precise distance. We need to complement Gaia photometry and spectroscopy. And we use astroseismology as an extra check. It can be used also for obtaining ages for very far away stars, but also as a check of the parallax shifts and so on, as has been done by other groups, by this group, but with other people. And so our hope is to get this map of the galaxy, but it's a multidimensional map. As I said, has all the kinematics, the positions, the velocities, and number of elements, depending on the instrument you are working with, high resolution, low resolution, and so on. So there's always a trade-off, because some things to see, you need statistics. Other things to see, you need detailed chemistry. And that's what is the difficulty. And the difficulty is that we have to construct this map, and we have to know that what I just said, that the stars I'm seeing, they can be moved. So the current position of the star, even the guiding radius, we take into account the eccentricity in the orbit, it doesn't mean the star was born there. It could be moved. And on the top of this, we have stars accreted from Gaia, Sagittarius, and other galaxies. So I just wanted to very quickly say that we enter into this adventure to compute the distance and extinctions, because we were also preparing the catalogs for most. Using Gaia DR2, soon after Gaia DR2, there was this map of the galaxy. You see the galaxy like if you're seeing it from above. You have X and Y, and in that region is where you essentially expect to see the bar. And the first distances were not showing this because was using Gaia only. Was decided to use for this paper Gaia only parallax and a model of how to take care of the distribution of the stars in the galaxy. And then that's why we also decided to be ready at that point to have this spectrophotometric code that we call Star Horse, that already in Gaia DR2, even if in Gaia DR2 we didn't have the best parallax yet, we could already see a different map. We could see a map where the bar was clearly visible. And that's the map for the same stars that we can see using Star Horse. Why? Because we are taking into account in Star Horse a lot of other photometry, including 2mass and WISE, and in this way you can break a degeneracy and have an idea of the extinction, and then have a better distance, especially when you are in high extinction situation, which is towards the inner galaxy. So every time we, in our project of Star Horse, every time we prepare such a thing, we made it public. So there is a database where you can download distance, extinctions, and all what we call secondary parameters, which are temperatures, log G, and so on. So that made that the Gaia simulated end of mission coverage of the Milky Way that is expected from Gaia from 3D maps would be like this. And we, by Gaia DR2, had already obtained this. Of course, it's not the same, but I mean, we were already expanding the 1/parallax volume. You could use 1/parallax volume only for the very low parallax that didn't have large errors, and that is only in a very restricted volume. It's below 1 to 2 kiloparsec. But to extend, which is our goal, we need to combine with other information, and that's what we did in this Star Horse project. So with Gaia EDR3, things got better. Parallax was improved, and also proper motion was improved. And we then went through the bulge, where we wanted to use the proper motions as well. And here is our map of the stars in the sky in this paper, where we then computed not anymore only to G18, but down to G18.5, and again obtain, thanks God, the same map, because there were a lot of improvements in between. There are other photometry we use, and so So we got this from the input up to G18.5. We had 400 million stars as input, and the code converged for around 350 million stars. And we release also the full. We release the full thing, but with what we call good flags of Star Horse are around 300 million stars. So these are 300 million stars that you can trust, especially if you are not in the inner parts of the galaxy. If you are in the inner parts of the galaxy, we had to make some shortcuts because, of course, there is no miracle. Only photometry and parallax will not hold the very everything in the inner parts of the galaxy. You need more. You need spectra. So if this is looking the galaxy from above, and this is if you look the galaxy edge on, and of course you see a hole here, and of course this hole is because Gaia is in the optical, and you're not gonna get information from Gaia when you are very extinct in high extinction regions. And for that we have been discussing the possibility to do Gaia infrared as the next Gaia mission. And so this is if you see now what Star Horse give you from far away. I just increased the scale now to a volume of 40 kiloparsec. And you have there Magellanic Clouds and Sagittario for which we have distance. That's what is showing. Just one very small word on Gaia infrared. So Gaia infrared, here you're seeing the number of stars that that there was a simulation expecting what you would have with Gaia infrared. But I think the more interesting, and this is all explained in this article, in this publication in 2021. But what is interesting is this, that if you compare the number of stars you see in the Gaia maps with respect to the number of stars you expect to see with Gaia infrared, you may have a factor of 8 in the region of the bulge. So you talk about Gaia is almost 2 billion, so 8 billion. So prepare your computers. Yes, the main goals of Gaia infrared is, of course, to probe the hidden regions of the Milky Way, which we were not doing yet, and improves on the proper motion, because the same mission 20 years afterwards improved the proper motion by a lot, and also to reset this reference frame. So this is ongoing, and I would love if you engage, because we need to be as a community wanting that this happen. It passed in the first, it's considered a mission, maybe an L mission, but it's still considered by ESA as a possibility. Okay, so this is what I show you is like the maps we could get 3-dimensional using extra information, Gaia plus photometry. But now if you get, you can get more if you have spectroscopy. And what is the first more you want? Radio velocity. Because if you have radio velocity, then you have the full orbit of the star. You have the transverse velocity given by the Gaia proper motions, and you have the radio velocity given by your spectra. So ideally, you want to have spectra of all Gaia stars. It's impossible, right? And because you're getting the spectra, you also would like to have the chemistry. So then it became even more impossible, right? So nothing is impossible, and we try to organize, the community organize itself to do this both from the north and from the south. And this is for most and WEAVE, and other projects as well were ongoing, right? Already when Gaia came up. So this is where we are going towards where we are going. So the first part of this project we just did now in 2023. So what we did is like we haven't started for most yet, and it's just started. Okay, so let's take all those spectroscopy surveys we have already, and there's a list of them: LAMOST, Gaia ISO, Apogee, Segue, Gala, Rave, and Gaia RVS when it became possible, available. And we now run the Star Horse to see cover the whole sky. We run Star Horse having as an input not only the photometry but also the spectroscopic parameters from the pipelines. We are still not in the ideal case. We just took the spectroscopic parameters preferred by each of the pipelines of each of the surveys and run Star Horse on it. We didn't do the homogenization of all these parameters, which is yet a huge extra job, and that should be done and will be done for sure. Hopefully not by me. So essentially here, what we managed to compute, and I don't want to spend much time because I wanted to show you some results. We managed to obtain distance and extinction for essentially 11 million stars that were in the spectroscopic surveys. And what is nice is that for around 2.5 million stars, we got also ages. How? Isochrone ages for stars that are in the main sequence turn-off or subgiant phase. We decided not to publish any age that was like in the giant branch. It's just like noise, essentially, okay? So in this sense, we were very conservative. So here there is 2.5, being conservative, there are 2.5 million stars in ages. So this is amazing. And here I am just putting a map of these spectroscopic surveys in X and Y, and you see where they are, how they are distributed in the galaxy. And you immediately see this magenta here is Apogee covering the bar. And Apogee is an infrared survey. So it's the only survey that really peers, not the only, but in terms of statistics, really peers and can add information not only in the bar of the bulge of the galaxy, but also very close to the midplane. Most of these other surveys are in cone shape, avoiding the high extinction area. There we are going to the plane like this to see the galaxy. So it was a new way to see the galaxy. Okay, so once we have 6D phase space information, chemistry and age, then we need to see something. And be that with all that, you don't discover something else. Okay. But you have a lot of caveats. I'm showing you beautiful maps, but we have one extinction law. For each of these papers, there is a section caveats. Okay, so we are always thinking maybe there is something wrong, or maybe could be better. So the approach would be to take different samples, and if you find the result, try to find it also somewhere else in another sample with another spectroscopic input and so on. So this work started, didn't wait for Gaia, and the work could have started already with, thanks to seismology, astroseismology of red giants specifically. Why? Because with seismology of red giants, you can get a mass, and you can use a model to transform into age. There are a lot of caveats also there, but we could try to see what does this give us. And of course, the first thing that we could use were Corot and K2, because these are sampling large radius of the galaxy and open clusters as well. So I just start with one example. Here you have a simple abundance gradient in the galaxy, iron and the galactocentric distance in the Milky Way. And here you have objects that are tracing young populations, okay? And if we take the ages for the Corot stars, which are the blue points, for the Corot stars that are younger than 1 gigayear, they sit over the Cepheids. So things for 1 gigayear are making sense, or 2 gigayears are making sense. Still, you have the gradient of the galaxy. So if the stars are dispersing, for now, in this galactocentric region, you see I'm only between 6 and 13. If I go to the inner part of the galaxy, it's different. But here, where I had the data, in 2017, that was the situation. So now I have this data here in 2017 for the present day gradient, but I can then walk in time and put at each of these columns different stars of different ages, because I have the age from the Corot. Here down, you see one simple chemical evolution model that you could run for a thin disk only. And on the top of it, a simulation where you allow for radio migration to take stars out of that line. And that's what you're seeing. The stars that come out of that line are radio migration. The older the star is, the more time it has to migrate. But it's not so linear like that. There are also chaotic situations where the star moves very quickly out. But this is to show you what we would expect from this point of view and what we are observing up there. And this middle one is if I mock this simulation to make the same as the data. And essentially, this seems to see that we are seeing radio migration happening, but could be other things. The error bars, especially the iron here, are very low because these are apogee error bars. And in Metallisti, apogee was a very good, it's a 20,000 resolution. Okay, this was back in the past, but this should also show then if I have clusters in the galaxy. That was for filled stars with age from Corot. Another data set for which we have age are open clusters. So if now I take the Occam apogee survey, which came in 2022, and I plot in the same plot for, of course, it's different because the age ranges are different for the clusters. But anyway, for younger than 0.4 billion years, from 0.4 to 0.8, and then for there is from 0.8 to 2 gigayears and older than 2 gigayears, you see that the clusters are essentially showing this migration. It's going a bit towards the blue data points, okay? And you start seeing that you could find at the solar vicinity an older open cluster that is more metal poor, more metal rich than a younger open cluster, which is the opposite of what you would expect, okay? Why? Because this cluster migrated from the inner part, it brings its high metallicity, while there was another here forming with a lower metallicity. And so this is old, has time to migrate. This is forming now and has less metallicity than the one that migrates. So this is also an indication that maybe it's really, we are observing radio migration, okay? Well, you can do this also with seismology to see if that's bringing you to the same result. So this is, again, showing the same models, more or less. The orange points are this same survey of apogee, and this green shaded area is the age computed for a sample in K2 by that was in this paper Villet et al. 2023. And what we see, K2 and apogee is always something that gives the age plus something that gives the chemistry here. And essentially, you start seeing the same thing. This as when you are at older situation, but now the baseline is much better than with the cluster because you can go older, you can reach 10 gigayears, right? So you're again seeing the same result. That's what I mean. Different samples are indicating the results in the same direction, but we are still like this, just the direction. Now we have to we are getting more and more quantitative. Then you can do another thing, and this is a more dangerous step that is being done in the literature, is that you can use for example, the seismic ages that, for example, we published for Kepler stars that had in the Medio et al. Paper 2021. We published these ages for Kepler stars with apogee abundances, and you can train with machine learning the other spectra or the rest of the spectra in apogee to get an age. Very dangerous step, but if you do that in the way that's explaining to this paper under the top 2023, and then you plot to see what this is giving me as the age of the full disk, that's what you get, which is more or less what you expect, okay? What you get, the disk get older as you go above the plane and younger as you are more on the plane. And in the outer parts, you have a flaring of the disk. That's why the younger population flares, and that's what's giving this. None of this was put in as it was just an outcome of using the seismic stars to transfer label the whole apogee survey. Of course, it fails in the inner part, and you see there is a chunk of the inner parts not happening, okay? And the reasons are discussed in the paper. Well, let me just go on because the rest we don't get there. Okay, so let's just see what can we get when we go to the more metal poor regime. I was only now showing that, okay, this age plus metallicity so can show you radio migrations happening in the disk. Now, when we go to older stars, so for example, if you go to this Queiroz et al. 2023 paper, where there is 2.5 million stars with ages, and you look to the Segue, which is a difficult survey because it's a low resolution, the stellar parameters are not that the best to use for some things, but has one thing, it goes deeper. And when you plot the alpha over iron versus iron for that survey with age, and you color by age, you see there is an excess of stars with ages and low, I don't know, do you see my cursor here? Yeah, you see here there's an excess of stars with low alpha over iron and old. But we all learn high alpha over iron if it's old, and when it goes down. So this means what? There's another system there, another system where the star formation was inefficient, and you can have a lower alpha even if it's old. And that's, so what is that? So there are several things you can study in this data set. This data set is public, okay? We made it public. But so this was, I made this one first to validate and to show as an example. So let's concentrate on what do we have here. So we have here Segue, Gaia, star horse distance. We get, we see that there inside we will have 1,600 string members of Sagittarius, and we can find, just like that, 200 very metal poor stars and several global clusters that was not seen before here in this sample. So because you have age. So we use this in this paper of Lindbergh et al., where we select by using this diagram angular momentum and essentially is angular momentum also LZ, and we select the ones that have that are more on polar orbits and not on radial orbits. So the Gaia and Sala disappear when you are more in radial orbits, and here is when you are more in polar orbits. And we see we had a lot of candidates Sagittarius here, and we studied those stars. So we studied this Sagittarius, and what are them? They are not there in the bulge. They are here. These are the Sagittarius stream when Sagittarius is crossing and plunging here. And you have two arms. You have the leading arm and the trailing arm. And it happens that we have a big, here you're seeing magenta, a model, dark, in the dark matter model, the stars models. And then you have on the top of that our sample. And we have stars in the trailing arm and in the leading arm. And for some of the stars, we even have ages because some of them end up in the mid-sequence turn-off. So for some of them, like for 50 or so. So you can constrain a lot about Sagittarius. We see, for example, that the trailing arm and the leading arm have different metallicities. It's just an example of how this data can be useful to understand even outside galaxy in extremely detail, okay? You can do more. As you saw in this other plot, I could select the polar orbits or radial orbits, and then if I go to radial orbits, I get Gaia Enceladus, only kinematically, right? And so I can now plot what is the alpha over iron versus iron of Gaia Enceladus and Sagittarius and the Milky Way, how they compare. This is what we are doing here. Here is extending, of course, the segue was important because it's extended in metal poor, it's biased to metal poor stars. That's what this was possible. And you see here, the leading arm, the trailing arm go of alpha over iron versus iron. And yes, it is at lower alpha, as expected. And is even below the one of Gaia Enceladus in this data set. And you can also find other weirdos, like we found some carbon-enhanced stars also there. Okay, so we provide the age estimates for individual stars in Sagittarius stream, thanks to a subsample of 56 stars that were turned off as subgiants. And we got an overall age of 11 gigayears, more or less. Okay, this was an example going super metal poor. Now let's do an example going the other way, super metal rich. What is super metal rich? Star that's above, I have age percent definition, but my definition above 0.2 in iron, okay? Almost 3 times, or it's less, 1.5 times of the solar abundance. Why is this important? As I said, the stars are moving and are appearing here, stars that are from another radius. And unless I have a way to find their birth radii, and there are people trying to find their birth radii with different ideas, one way to get rid of the problem is to look for the super metal rich stars, because they could not be formed here. They should have been formed inside the galaxy, somewhere inside, right? And so I can use them as a kind of the ones I know their birth rate, more or less. I know their birth rate should be beyond the in the inner 2-3 kiloparsecs. So I don't need to calculate. I know it, right? Of course, you say, ah, well, could it happen that there is a super metal rich star forming here just today? Can always happen. But the statistics, the reservoir of the super metal rich stars, and I'm showing you in a while, are in the inner parts of the galaxy. Is in the inner part of the galaxy. So The first thing is at the solar neighbor. At the solar neighbor, using apogee and Kepler, we are sitting here. The field of Kepler is a bit above the plane, so we are more biased to thick disk stars. And when we got to the ages with uncertainties around 25%, we could do the MDF, the metallic distribution of the stars here in this sample, which is Kepler plus apogee. And we see that the most metal-rich stars are not the youngest. Well, in a chemical evolution where the things do not mix, the end point is the most metal-rich star. If you know, the metallicity is increasing with several generations, so the recent ones, the most metal-rich should be the youngest. And the data tell you, no, it's not. The most metal-rich are old or intermediate old. Why? Well, because they are not forming here. They are forming in another radius and was brought here. So it's again radial migration. You see this, and you can quantify this. Okay, so where did they came from? We're gonna answer this question. Okay, so you have the gradient. Well, but some of them are beyond what the gradient can give you, and you don't know the gradient beyond certain radius. So you have a problem because the gradient, mostly of the data set trace the gradient from for outside. So you don't know exactly. So let me just pass this. So you want to know where are those stars. Now we have, here is what I showed you in the beginning of the talk, the photometry plus Gaia. And when we go to that square, which is the inner part of the galaxy, you need the spectroscopy. Otherwise, your distance are not that level what you need. And that's what we're going to do. We're going to use then, here in this box, I have 30 million targets. And in that box, which has spectroscopy from apogee, I have 30,000. That's the price you pay, okay? And you're going to pay another price. That's the extinction that Star Wars computers really like inside, and it's on the mid-plane, and it's huge, you see? So what will happen is that I need the proper motions of Gaia as well. So that means I will lose a piece of my sample, because for some stars I have apogee but do not have Gaia. Until 2050, when we were going to have Gaia in the infrared, and I'm starting doing gym now to be able to be alive. Okay, so why do we go there now? Because at this point we had Gaia EDR3, and Gaia EDR3 improved proper motion. So each science project follows the next of Gaia, okay? And this is showing you the improvement for the sample, a sample that we are doing very inner galaxy between Gaia DR2 and Gaia EDR3, the improvement in parallax error and in proper motion error. So we have an improvement, especially in proper motion. So now you can do this plus that I don't want to discuss, but it's the alpha over iron versus iron all over the galaxy at different heights from the mid-plane and at different distance from the inner galaxy. But I wanted to focus here in the inner parts of the galaxy. I wanted to find the distribution of the stars there to see their metallicity, okay? When I go to this sample, that is a very inner sample that we call RPM, which is, we use the proper motions to also select and not to fully rely on Star Horse. First thing I see is this pattern for velocity, radial velocities in the inner parts of the galaxy, showing this kind of this pattern here you are seeing in radial velocity. That is what you expect if you had the bar in a very great detail. Also, the other side I can see with this sample. And this is what you sometimes see also in some simulations that have bars. Okay, I will jump this part, but essentially I need a proper motion and a good distance. That sum of 30,000, when I take the disk from the front and I am in the bulge, I am left with 8,000, okay? So price to pay. But for this 8,000, I have the full orbit of the stars. Then you say, oh, but which potential you use? Because I'm computing an orbit in the inner part of the galaxy. So you have to, this is also a caveat you have to worry about, and we discuss this in the paper. So essentially we take that sample, and now you are in the bulge, and you cannot be saying this is thick this is thin this. You don't know. You cannot use the usual way to separe things we use in the Milky Way. You have to just project this in this kind of diagram, which is a Z-max eccentricity diagram, and see at each of these windows who is dominating each of the populations. And you find the essential. So here we went from 30 million, 30,000 to thousands, but we find that in the inner parts of the galaxy, we essentially find an inner thick disk, an inner thin disk, and an old spheroidal bulge, and a big bar. Let me just move this. Okay, the stars that are at low Zmax in the inner part of the galaxy have this alpha Vellarum ratio, and the ones that are in red are the ones that are in bar-shaped orbit, according to this potential. And what is interesting is that as the centricity increases, you get more stars, of course, that are in bar-shaped orbits for this sample, but you see also that stars are in bar-shaped orbit, both in the high alpha and in the low alpha. While there was an idea inside the community that you would find that all the low alphas are the ones that make the bar, and it's not the case. But to come back to my point is the metallicity distribution function. The metallicity distribution function of these guys here, which have guiding radius of 1-2 kiloparsecs, so really like inside the galaxy, they have metallicities. Look at the peak that they have in metallicities above 0.2. The galaxy has a reservoir of even the inner, in this case, more metal rich as we expect, but the ones that are in the bar are even more metal rich, and you have a big reservoir of very metal rich stars in the inner parts of the galaxy that can well be kicked out from there to here. Okay, so let me just jump this. Okay, now we went here, got the ages, saw the super metal rich, gave age to them. They maybe come from the bulge. I went to the bulge, but I don't have ages. That's the problem. I don't have ages in the bulge. I have there is a sample for lens stars, but it's a small sample of ages. Otherwise, the ages in the bulge come from CMD. Another way to get the ages from the bulge, this is the kind of extinction you have in this region that we are interested in, is globular clusters. So here you have a set of bulge globular clusters in the very inner parts of the galaxy. And for this globular cluster, in this collaboration with Beatrice Barbui and Souza, you can plot the globular clusters in the same kind of diagram we have for field stars, right? The difference is that for the globular cluster, I have a very good age. These globular clusters all have HST photometry. And the ages are essentially, the globular clusters in the bulge are among the oldest objects in the Milky Way. So they are above 30 gigayears. And if I plot them in an age metallicity plot, they are really showing a very fast enrichment situation where the metallicity has increased very quick in a very short time scale, just like we think an old bulge will be the case, will be doing. Okay, and of course, you have then to use chemistry to decide also if they are in situ or accreted globular cluster is also another thing that is complicating the scenario. And I wanted to close with this last result, and I actually there are two results, but I will close in this one because the next one I do not want to spoil the results of my PhD student. So with Samir Nepal, and we'll be presenting it here in the conference. And so it has two recent papers. It's on the AstroPH, and I will just briefly say. So here was the first letter. So as I said, we run in different projects depending on what Gaia is giving us. In Gaia DR3, it became available RVS, so spectra for a lot of stars nearby. But these spectra are in a very short wavelength range, and so there are some difficulties if you use only spectroscopy to obtain the stellar parameters. However, Gaia also gave you the XP coefficients. Okay, this is extra information. So what we did, we embarked in a machine learning project where you combine the information from the spectra and from the XP. And this gives you the possibility to increase your sample. So if I go only for the spectra, which is the Gaia publication of Hessio Blanco et al., I should have put it here somewhere. Then if I do the flagging cleaning, I lose a lot of the sample because I have to be working at high signal to noise, higher signal to noise. The XP spectra in the machine learning helps me to get good parameters also for lower signal to noise and increase statistics. And then you can go to some projects that you need the statistics. One of them is the supermeteoric stars. Why I need statistics? Because they are rare. They are rare. And so to have a good sample of supermeteoric stars, I need the large statistics. And that's what in this paper we do. We have almost here 170,000 stars within 1 kiloparsec. The niche of this sample is that is within 1 kiloparsec, so the distance is extremely precise. Parallaxes hold the distance. And the distance we are getting here with Star is like 1% precision. So you have these two as an extra thing that you can use. And then you have a bunch of them here, you see, in the main sequence turn-off and subgiant phase. And so you're gonna have to, we can obtain ages for them, isochron ages. So this is the machine learning that is explaining another companion paper by Guillaume et al. 2024, who also will be here in the conference. And essentially, here is what we see as a result. If we plot for this huge sample of metal-rich stars, the metallicity versus the age is not an age metacylation. It's just the, let's say, the 30 or 40 most metal-rich stars in each being of age. Not 30 or 40, I think it's more. And you see that you're seeing the envelope of the super metal-rich as a function of time. And what you're seeing is that at some point, which is marked here yellow, the super metal-rich stars are not coming anymore here. This is a very close by volume, 1 kiloparsec around us. So they disappear of the sun. So why is that? Is a bias of our age? This is all discussed in the paper, and we think not. We think this is corresponding to the last time the bar punched the stars here to the solar vicinity. So the last bar activity moment, and there is a lot of justification why we think that. But first of all, let's see if we trust our ages. So as I said, we then take the ages for a similar sample, but from seismology, and see if we also see there of super metal-rich stars at some point in the galaxy coming here. And we see a similar drop in the seismic data, very similar to the data we have. So the idea is that if some people have some models that say at the moment that the bar have this activity, and I'm not an expert here, it can dump energy into the gas, and you can form an extra star formation rate episode. And we think we see a bump there. I'll show you where, which correspond exactly to just after this drop in the supermetal-rich star. So it's like the supermetal-rich star was being sending here, stop, and that corresponds to a very interesting peak in the star formation. This peak is at an age that does not correspond to the peaks that are seen related to in relation to Sagittarius. That could be an alternative explanation. And this is a little bit alpha-enhanced as well. Okay, I said I will not spoil these results. Essentially, we use this sample, which you have 565,000 stars with 6D phase space, very good distance, to look for the very metal poor stars in this sample. Very metal poor here is below -1. No, it's not very metal poor, it's metal poor. Depending who is. And then to study mean sequence turnoff and age. And essentially, we find these very metal poor thin disk stars that are metal poor and are in very thin disk orbits. And then because we have age, we are able to demonstrate that we actually are not only seeing the metal poor thin disk, there is a thin disk, very old in the galaxy. And that's the kind of discussion I want. So V5 versus metallicity, there is a lot of stars in V5, quite high. They shouldn't be there, metal poor, and they are what we are calling the thin disk of the Milky Way. We thought the thin disk of the Milky Way was not that old, and we show in this paper that is really old. And to confirm the other groups that had been seeing spots of this old thin disk, but here with high statistic, you see a lot of them. So it's very hard to not to believe they are there. Okay, so let me just finish. This I just wanted to say that if I compute the velocity dispersion for the stars that are in this old thin disk, they are very similar to what is being coming out as a velocity dispersion from observation of ALMA disks at very high redshift. But as I said, I will not go much here. Okay, so I will finalize by saying, okay, you have all that, what do you need for most? Okay, and the answer is that the coverage of spectroscopy is much larger in the northern hemisphere than in the south. In the south, you lack data. And we are going to complement this region here of the data. So what is for most? So has two sets of resolution from 4,000 to 7,500 and 20,000, and have more than 2,000 fibers. And that's inside for most, there will be our project called Formidable OR. Essentially, we complement Gaia with radio velocity and also chemistry. Okay, this is the spectral range of the high resolution. And this is our survey. The co-PI is Ivan Minshev. And where we are putting our coins is the fact that spectrograph of low resolution can still give us some chemistry, because the wavelength range is very large. And so we are making tests of using machine learning to see how to recover chemistry from the low resolution. And CNN pipeline that we use for these papers that are coming now, apply the CNN method, this machine learning method in the RVS data, is in preparation for a pipeline that we hope to have working for most low resolution data. So how are we going to cover the galaxy? Well, it's not easy, because it's not a galactic archaeology per se. We are inside a very complex system where we have science in parallel, doing all kinds of science. So we have to divide the galaxy in some way. And so we have what we call the ESN, which is here around where's the best of Gaia, essentially mimicking the work I'm doing with RVS. Then we have the disk, most what we can extend down to magnitudes. It was 19, now it's shrinking. It's becoming 17.5, almost 17. And one part of it we call CHEM, which is a part of the disk targets that will have more signal of noise, for which we hope to get the chemistry. This is also being shrink, unfortunately. And the big, which is the bulge inner galaxy part. That will be a huge thing where we got more exposure time in the inner parts of the galaxy. For most, it's becoming reality. The first piece was sent to ESO just now. Okay, it's one piece, but okay. It marks the first one that went, is this cable wrap. Here you see the VISTA telescope, the 4-meter telescope where the foremost will sit. And the instrument that was there, the camera was already taken out, so we are in a pressure to not keep the telescope empty. Yeah, so in particular for the inner galaxy, so here you see the galactic longitude, so 35 to, so the inner part of the galaxy. Then you see the BDBS footprint is the bulge, the Blanco from Mike Rich and collaborators. You see the region that they are going to. And this is, we are going to cover this with the big. And so we hope, I leave for here some key points. I would like to just summarize that by combining the Gaia with spectroscopy, we can then get this precise distance. We are seeing also this radio migration happening. The bulge now can be starting to be studied in orbital space, orbital chemical space, which opens, and I could not talk here about the bulge because it takes a full talk about the bulge. And the objects that are confined in this 4 kiloparsecs show this metal-rich, very metal-rich thin disk with IMDF peaking at 0.2. So there was a discussion if metal-rich would go down, so that's not the case. And the globular clusters is our really stones that show, well, that galaxy, our oldest stars in our galaxy, is really giving us this view of the universe in the very early moments of the universe. It's a total complementarity way to see as you are getting now for JWST and ALMA. And we have there a reservoir of migrators. They are migrating, so we need more models of the inner of simulations that have bar, that have gas, and maybe that are cosmological. So yeah, there are some, but there are difficulties in each of them. And we have confirmed the existence of this old thin disk. Most of these thin disk stars are older than 11, 12 gigayears. So it's really this old disk was already there, maybe preceding the thin disk, the thick disk, sorry. And what is this? Is the stars from the bulge put in this orbit? Is this really a disk? That's a big discussion right now. And we have the age challenge. The age challenge stays because there is only 2 ways. One was Haydn, and it was, but maybe it will be. And so I don't know. We had a very good project to do astroseismology in dense fields and to explore what we will learn from seismology in clusters to then constrain better stellar evolution things that we still have to be constrained, and then apply to the bulge and get a sample in the bulge of 70,000 stars of age. I get like what is not happening. I don't know. So I got this because I could do a diagram for you with seismic age with 70,000 stars. Can you imagine what we could do? But okay, so we don't have this right now. What can we have? So we have Plato, but there are only a few giants there, and they are for calibration, so they are not going to get there in the bulge for now. And then the last hope, and it's the hope that is the most strong one, is on large telescopes. Why? We want to then get to the bulge and go down and see the main sequence turn off and subgiants with all the difficulties that this will bring, crowding and so. And for that, I helped to write the science case here inside this beautiful paper that a lot of people has contributed, which is the WST telescope as out on AstroPH. This idea to have a big telescope and to have spectroscopy and to really reach these main sequence turn off and subgiants in the inner parts of the galaxy. I don't see another way, and maybe also another good thing is LSST. Are the projects in enlarging the coverage also into the bulge area. Original plans were taking out fully the midplane, and now this is including the bulge and that area. So, and moons. I mean, really, we are, and we have the so. I think the community is really trying to get the grips in the bulge and to understand better the impact of what's going on in the galaxy, bar and spiral arms that are coming here as well, as you saw. There are many stars here. Okay, thank you very much.